Okay, so welcome to class 12, and we will be discussing canonical ensemble. That is a system uh, where where the system is in contact with a heat bath, and the collection of microstates that this system, the smaller system which is in contact with the heat bath, the collection of uh, microstates that it can take, and the properties of the of the set of microstates is what is the canonical ensemble, and that is what we're going to discuss in today's class. So our aim is to have a better physical understanding, insight of the canonical ensemble. And what I had already briefed in class 7, I think, is that the probability that the system is so which system are we talking about? Let's talk about such a system. This is the entire system which has a reservoir, suppose the city of Pune, and a room in which we are sitting, and suppose there's no AC, uh, is the focus point. So this classroom or this room where I'm sitting, which is in contact with the city of Pune, which is acting as the reservoir, and we are interested in looking at the properties of this system, uh, which can exchange energy with the reservoir. So the number of particles in the system is n, the volume is v, number of degrees of freedom. If it's a gas, then basically the number of degrees of freedom is 3n space and 3n momentum coordinates, right? So that is F, whereas the reservoir has the degree of freedom capital F, and the reservoir is much bigger. The city of Pune is much bigger than uh, the system in consideration. Suppose this room in consideration, and this entire system, the system of reservoir plus room, or the city of Pune plus room, this is considered to be in an isolated system. Now you would know that the city of Pune is not an isolated system. It is in contact with, I don't know, the neighboring districts, the neighboring towns, the city of Bombay, and so on and so forth. But with respect to this room, which interacts only locally and which is much smaller than the city of Pune, it is interacting only locally with this entire reservoir, right? So it doesn't even know where the end of this, where the end or the boundary conditions of this reservoir are. It is exchanging energy only locally. And if we consider this reservoir or the city of Pune to be an isolated system with a huge number of degrees of freedom, it really doesn't matter to the room because it's exchanging energy only locally. And what we are talking about, or what we had said in the class 7, is this room with a fixed number of particles and a fixed volume, but energy can change. So it can have different values of energy Ek, and the probability that this room, this system, the smaller system, occupies a particular microstate with energy Ek, the probability that this room will be in a particular microstate, and being in a particular microstate is extremely important as different from energy, is in a particular microstate K, is proportional to the exponential minus beta is 1 by kBt into Ek, or exponential minus Ek, where Ek is the energy of that particular microstate by kBt. Okay, so Pk is the probability that the system here, the smaller system, the room system with degree of freedom F, has energy Ek. And the question we are going to discuss is how does this come about? How do we know, why do we? So this is also known as the Boltzmann factor. And how does this come about? So why is the system having contact, having thermal contact with reservoir? Why does it have probability of the system being in a particular microstate of energy key? Why is this possible? Whereas remember, when you were looking about in the microcanonical ensemble and an isolated system, all the microstates had equal probability. But suddenly, when we are looking at a system which can easily exchange energy with a huge reservoir, the probability that different microstates have are different. And higher energy microstates are penalized. They have lower probability. How does this come about? And that is the topic of the discussion. As I have said, so this is in contrast with an isolated system, the microcanonical ensemble, where the probability that the system is in a particular microstate was all uniform and was equal to 1 by omega, the total number of microstates. Each microstate was equally probable. All the probability of occupying each microstate was all equal, right? And this is to be contrasted with this. So this is the topic that we're going to discuss today. And the other thing which we have discussed is we have already discussed the microcanonical system, the isolated system in some detail after class 7. And what you already know that the 3n degrees of freedom that the system, of course, can occupy, especially if we're talking about an ideal gas, they can occupy, each particle can occupy any space, any point within the volume. And moreover, the momenta degree of freedom, they can explore different microstates, and the number of microstates only with respect to the momenta degree of freedom goes as 2me to the power 3 by n, right? Because it was basically the surface of a hypersphere. So it was actually the volume of a thin shell is in 3n-dimensional space, a spherical shell, a hypersphere, and the surface and the volume went as 2me to the power 3 by n. Right? Even if it is 3n minus 1, if you want to talk a shell, it's still 3n minus 1 equal to 3n because n is very large. So that's what we had discussed. Here, just to give you a better meaning, just discuss about this in a better detail. Suppose that the momenta, so suppose there are n particles. N particles is the degree of freedom. Just let's focus on the x degree of freedom, right? So the total energy available is 2me. The sum of the kinetic energies of all the particles for an ideal gas is 2me. But the number of ways that each particle can take different values of momenta, so which can be called L, and L by n is much larger than 1. Why is that? So basically, suppose one particle can have a very small value of momenta, or slightly larger, and the number of ways that each particle can take different momenta is order of, it's not equal to, but order of 2me, the total basically energy of the system into 2m. If you multiply the kinetic energy into 2m, it's p square. And basically, if you take a square root of it, right, you get basically an idea of the magnitude, right? And you're dividing it by delta px, and delta px is suppose the precision on the momentum in the measurement of momenta. So it can have a huge different values of momenta, and each particle can occupy these different values of the momenta, provided the sum of their kinetic energies is kinetic energy is E, right? So hence the number of ways, this L by N, L is the different values of momenta that each particle can take by the degrees of freedom, N is very large, especially if E is large. If it's not, E is really near the ground state, of course, then all particles have zero momenta. So I'm not talking about that. I'm talking at the finite temperature, E is large. So each particle can be in various L states, and the point is that also that the various N particles in that case can be in 2me by delta px, basically L to the power n states. And of course, if they are identical, you can put in an n factorial, and the number of microstates available are absolutely huge. Right? It's like exponentially increasing. And of course, so because even if you take this, if so exponential would of course have all the sum of 1 plus x plus x square and so on and so forth. But since L by N is so large, and if you put in this factor, the precision factor here, this number would essentially dominate over all the previous terms in the sun, and so hence I'm writing that as an exponential, right? So this is a slight deviation, but just to give you the huge number of microstates that are possible, and they're absolutely hugely increasing with e to the power n, right? But as you increase e, the number of microstates goes on increasing exponentially, but also that the probability of occupation, especially if it is in a canonical system, not especially if it's in a canonical system, that probability actually decreases. And there's a balance which is achieved, right? So that's the message. So just to repeat that, suppose there's a reservoir with capital F degrees of freedom. F degrees of freedom is much greater than the degrees of freedom small f of the system that we are interested in, and we are interested in looking at the properties and the number of microstates, how the system is, which microstate will the system occupy. So that is what we are interested in, because if we get that, when we can calculate thermodynamic quantities, as you shall see in 1 or 2 days, right? And the F total, the total number of degrees of freedom is of course F plus F, the total number of degrees of position. Now the point is the probability that the system has energy Es, the smaller system with energy Es, is also the probability that the system R has energy ER, and corresponding to ER, there are fewer number of microstates. Since the system has given some energy to the, or rather the reservoir has given some energy to system ES, the number of microstates available to the reservoir actually decreases. Yeah. So suppose the sum of energy reservoir plus system is E0, ER plus ES. Yeah? Then the number of microstates which is available to the reservoir with energy ER, there should be a subscript R here, is is ER to the power capital F. On the other hand, the number of microstates accessible, I mean, suppose you fix the energy, right, of the system, is e to the power S to the power F, small f. Now, F is much greater than F, this capital F is much greater than small f, right? So the number of microstates available to the reservoir is going to be much more than the number of microstates available to the system S. And if this ER is more, then a larger number of microstates is available to the reservoir. And then, and then, I mean, if the system has energy ER, then all the microstates with energy ER are equally probable, right? So the probability that the system has energy ES is equal to the probability that the system has energy ER. And the probability that the system has energy ER, that will depend upon the number of microstates that the reservoir can access with energy ER. That is proportional to omega, number of microstates, E0 minus ES. And if ES is small, then omega R will increase, right? Because the reservoir energy will increase, right? So this is the key point. This is the key point. Whether this system can access energy ES or not depends on the number of microstates that is available to the reservoir when it gives away energy ES to the system. Larger the number of microstates available to this, that has a higher probability. So the probability of this system having energy ES or being in a microstate with energy ES really depends upon how much energy is being given off, and correspondingly how many microstates is available to system R, which in turn decides the probability that this system will give energy ES, R will give system to S. This is the critical point. And what we do is write down, so as the reservoir gives energy ES to the system S, right? So how does the number of microstates change? So that's the question we are asking. And instead of calculating with the explicit factor omega, we are taking a log of it. Log of omega, we are rather saying how does the log of the number of microstates change as the system R gives energy ES. So the reservoir gives energy ES to the system. And this is a more slowly varying function. So we can analyze it better. So we are taking the log, and this log essentially, so this of course is less than ln of omega R when the reservoir R had the entire energy E0. So this log is when this is the log of omega R E0 corrected by how much? Del del E of log, the rate of change of this function, or rather this function, rate of change of this function with E into delta E, whatever energy has been given to the reservoir. And how much energy has been given? That's been given energy ES, right? And it will decrease plus higher order terms. Now, if we multiply this by KB, we know that this is like the entropy, right? And del S del E is like 1 by temperature. So what we get is log omega R E0 minus ES equal to log the R E0 minus kBt, and this is property of the reservoir because you are really taking omega E0 del E. How does the number of microstates of the reservoir change with respect to E? And of course, we have to show that it doesn't change much when you give energy off. So this is a property of the reservoir. It is much bigger than the system, and then this thing is P, right? So then we can rewrite this as log. So we are just taking this on this. So we are taking this. So we are just readjusting term, right? And then what we get is that omega r with a lesser energy by omega r with a larger energy goes as, and when you take the log of it, Es by kBt, right? And if we ignore the higher order terms because Es is much lesser than E0, then we get this relation. So basically we remove the log and put it in exponential, and exponential Es by kBt. But remember, so that is the probability of one of the microstates with energy Es. So that really depends upon the number, this ratio, and this basically gives the probability that the system R uh, has energy E0 minus Es, and that decides whether the system, so this is the energy of the reservoir, whether the system will have and can access a microstate with energy Es. Yeah, but remember that there can be multiple microstates of S with energy Es, and all of them have probability proportional to e to the power minus Es by kBt. As any of those microstates, and they are independent, are decided by omega r E0 minus Es, basically a low value of energy of the reservoir. So the probability of that the system S is in a microstate with energy Es is proportional to e to the power minus Es by kBt. But note that system R, the reservoir, can have can also have the entire energy E0, right? And the system S has zero energy, or it can have energy. If it gives some energy to the system, the reservoir can have energy E0 minus Es, or E0 minus Es dash, or E0 minus Es dash. So these will all be different microstates of system Es, right? So the probability that system S is in a particular microstate with energy Es depends upon the total number of microstates of system R, and that is proportional to e to the power minus Es by kBt. So this is the crux, that the system is in a microstate with energy Es, and that depends upon the number of microstates accessible as a consequence to the reservoir, and this can be shown as e to the minus Es by kBt. So that's the key, that's the reason. But there are buts. But before we come to buts, the probability that the system is in a particular microstate with energy Es is proportional to e to the power minus S by kBt, and the normalization constant is then sum over all possible microstates with energy Es, Es dash, Es double dash, and so on and so forth. But remember, even for a particular value of energy of the system, there can be many microstates. So you are summing over all possible microstates with energy Es. Moreover, you are also summing over all different microstates where the system has energy Es dash, and that can increase very fast, right? So the number of microstates itself can of the system can increase as Es to the power F. And if it has more energy, suppose Es double dash, then again the number of microstates of the system will increase. So we are summing over all possible microstates with various values of energy of the system, and the normalization constant is this sum over all microstates, and we shall call it partition function later Z, and it will be related to the free energy. But even before we come to that, the question that we ask is, so this normalization constant is Z, partition function, but let me clarify this. Since each microstate the probability of occupation of each microstate is 1 by Z into e to the power minus Es by kBt, does it mean that a microstate which has zero energy, all the energy is in the reservoir, that has the maximum probability of being occupied? The answer is no. So it is not necessarily that the system has to have energy zero. Why? Because as you increase the energy of the system, the number of microstates accessible to the system also increases. Okay, so the total system reservoir plus system, we shall consider it isolated. It will be in equilibrium only if the number of microstates of the total system R plus S is maximum. That's the condition for equilibrium. So we are taking the entire system to be isolated, and that has to be the maximum. And if all the energy goes to R, then the number of microstates of S decreases. Now, each microstate has lower probability, agreed, but also the number of microstates is increasing as you give more energy to S. What is necessary is omega R, the number of microstates of reservoir, into number of microstates of system. They must be maximum. And that maximum we have shown in the past that that condition is reached when TR, the temperature of the reservoir, is equal to 2S, because they are in thermal equilibrium. So if R will give some energy to S so that S can occupy a large number of microstates, then omega R into omega S will be the maximum. Now, what is that value? That's what we have to figure out. On the other hand, if this was the system and it had all the energy E0, agreed, with a much larger F, this system has energy 0. So all particles have 0 momentum. So that's only one microstate possible, right? So omega S will be very small. So that was not the condition for equilibrium. Agreed that each of the microstates accessed by the system has probability proportional to e to the power energy of this microstate by kBt, and kBt is a property of the reservoir. It has many degrees of freedom. So even if it gives some amount of energy to the system, its temperature doesn't change, and we shall discuss this more in later. But if it has all the energy, then this quantity is going to decrease. So what is important is that R gives some energy to the system S so that this product is the maximum. The probability of each of these microstates is very low. But if it has a large number of microstates, then the system can have a significant probability to have a fixed amount of energy. It need not be always 0. So what is the message? Just to summarize and repeat, as ES increases, the number of microstates available to S also increases, right? And if it has energy ESN, then its microstates, then the number of microstate will increase as omega S e to the power n, which depends upon the energy of the system, and the probability that the system is in a microstate. So I should write in a microstate with energy ES. Oh, sorry. The probability that the system has energy ES as different from a microstate is actually a product of, right, the number of microstates that is available to the system when it has energy ES into probability of occupation of each microstate. Now, the probability of occupation each microstate might be low, but if there are a large number of microstates available to the system, omega SES, right, then the product of the two can become significant, and that the system can be in a particular energy ES, need not be close to zero, because it's this product that matters. And note that here I have discussed that the system has energy ES, and there are a large number of microstates corresponding to the energy ES, and that is different from the probability that system S is in a particular microstate, right? SK. So K is a microstate, and that is proportional to e to the power minus beta ES by Z. But this is that the system is an energy ES, and that will have a large number of microstates also corresponding, and it is this product which will decide whether the system has energy ES or not. System has energy ES versus the system is in a particular microstate with energy ES. These two are different. And that the point that you need to understand that this function, omega SES, is a sharply increasing function with increase in ES, right? It's e to the power F and so on. E to the power minus beta ES is a sharply decreasing function. It's an exponentially decreasing function with increase in ES. And what a consequence of a product of a sharply increasing function and a sharply decreasing function is this product, the probability that the system is an energy ES is a sharply peaked function. So let me schematically show you, and this is basically figure 6.2.2 of Rife. And what is being said is, suppose omega S is a sharply increasing function, this solid line blue, it is increasing with E. So this is the probability. So the probability, well, this is just the number of microstates, this blue line, and it is increasing very fast with E. And we are talking what is the probability that the system is between energy E and E plus delta E. On the other hand, as E increases, exponential minus ES by KBT also decreases incredibly sharply, and it is an exponential drop. And yeah, so what was I saying? So it is an exponential drop so that the product is actually extremely sharply peaked, because this is very low value here, this is very low value here, and only at a certain point is there a very sharp peak here. Okay, and the ES, the value of ES will be such, it will be decided when del omega S del omega E, right, which is like 1 by temperature, and this rate they are equivalent, right? So the question is, how sharp will this be? So I have qualitatively given you an understanding of how sharp will uh, this product be, because this is very low values here and sharply increasing. This is very high value, but it is decreasing. So this will be extremely sharply peaked, because only at a particular value, well, the product of the two will have a reasonable value. And so the average that the system will most of the time spend energy near the maximum. So deviations away, or delta E, the deviations away are going to be relatively small. So that you can understand intuitively, that you are in this room, right? It is not true that the temperature suddenly, or sorry, the energy of this room suddenly increases or suddenly decreases, especially because it has a large degree of freedom. Most of the time, you will find that the energy of the room is something similar. That's your intuitive idea, because if energy of the room suddenly increases, you will suddenly feel hot, and the next moment you will feel suddenly feel cold, because the total kinetic energy, which again decides the temperature, as you shall see, is related to the energy of the room, right? So this room is always maintained at a reasonable energy, and deviations away are relatively small. And the reason is because this product is a very sharply peaked function, right? Uh, and most of the time, the system spans very close to the peak of this product. That most of the time, the system is actually has a certain value of energy, and away fluctuations away is very less. We'll talk about quantify the standard deviation, the delta E, the fluctuation in energy, in a later way, but this is the intuitive way to understand it. And before I end the class, I will just give another intuitive idea of what is happening in terms of microstates. Now, suppose we have been talking only about gases, but let me give you another example. So let me give the idea of ferromagnetism. I know that you have not been properly taught. I mean, might have known about domains and so on and so forth. But what ferromagnetism has is basically a system. Suppose you have a lattice, you have a solid, and at each lattice point, you have a atom sitting there, each with a magnetic moment. Now, for ferromagnetism, for reasons that you should understand a bit later, each atom or each magnetic moment on each atom also interacts with its neighbors, with, say, suppose energy J. So that if two spins are up, then it gets a negative energy, minus J. Now, each spin, if you are considering in 2D for simplicity, because it's easier to visualize it in 2D. So this spin has four neighbors, or rather each spin has four neighbors. This spin has neighbors this, and if they are pointing along the same direction, it has energy minus J, its energy is minimized. So all spins want to point in the same direction. And this spin has neighbors here, and this spin is also neighbors here and here. So these are the four neighbors. And you can either consider this system to be infinite, so that there are very few neighbors at the boundaries which have fewer number of neighbors. So you basically say, okay, you are really looking at a huge system where most of the atoms are sitting in the bulk, where each atom has four neighbors. If it's a 2D, of course, if it's 3D and it's a cubic lattice, it will have six. But get the picture. So you can either neglect the boundaries, or you can incorporate the boundaries, as we do in computation simulations, and many of you are taking the computational physics course, that you consider periodic boundary condition, that this spin is interacting with this spin, and also this spin, which is on the other side, because it's periodic boundary, it's like a loop, it's connected. So this, it's like a circle. And this, in that case, what it does is each particle has each part. I am recording. May I call you back in some time? I'm recording. Yeah. So what I was saying is Yeah, so each of these spins, suppose, has so basically the boundary effects are the effects of the boundaries can be get rid of, because you're considering each spin now having four neighbors, including the one in the boundaries, except that this one, instead of interacting on the left, is interacting with this one. In a real system, in an experimental system, anyway, the number of atoms of the boundaries are an insignificant fraction of the number of spins sitting in the bulk, right? And that is necessary, and that is the idea to keep in mind. And the ground state, the minimum energy state, and this system is in contact. So this is your system, and this is in contact with the room, which has much higher energies. Uh, Sorry, the room is a reservoir, so this system is exchanging energy with the reservoir. Now, its energy will be the least if it has given all the energy to the reservoir, right? It's this picture. So it will, if it gives all its energy to the reservoir, right, it will have the minimum energy, the ground state, if you like. And that is the state when all spins are pointing up. This has the minimum energy, the reservoir has all the energy in its possible. That is possible, and it has the largest number of microstates. And in this case, and suppose each interaction is minus J, it's negative, so the system, the energy is reduced if two spins point in the same direction. If it's so, and each has four neighbors, hence its ground state energy is minus 4 Ng. However, so this is the so-called Ising model, where two spins pointing up has energy minus J, two spins pointing down has also energy minus J. So basically, two spins, if neighbors, if they point in the same direction, there's a minus J. However, if the two spins point in opposite direction, that costs energy. There's a plus J energy cost. Now, if you give to this system, which is in ground state, and energy equal to 4J, because if this spin, suppose this spin flips, right, then this will cost J, this will have energy J, this will have energy J, this will have energy J, and this will have energy J. So instead of minus 4J, now it has plus 4J. So if you give energy equal to actually 8J, so this is not 4J but 8J, because the energy of interaction is 4J and it was previously minus 4J, so energy difference is minus 8J, right? So then one of the spins can flip, and of course its probability is e to the power minus 8J by kBt. So it's a low probability, assuming J by kBt is large, let's assume at the moment. But how many microstates are possible? This spin could flip, or this spin could remain up, and this spin could flip, or the flipped spin could be in any n of these sites, and each of those microstates are possible with probability e to the power minus 8J by kBt. And you have a huge number of microstates which are possible, and each contributes e to the power minus 8J by kBt, right? So, because you have a large number of spins, and hence you will have a large number of microstates which are possible, where only one spin is flipped, but it could be any of these spins. The product of the probability can be a reasonable number, even if 8J is much larger. Suppose exponential minus 8J by kBt was a very small number, but that is being multiplied by the total number of microstates. The total number of microstates is that this spin can be in any of these lattice sites, and it will correspond to a different microstates. So total number of microstates is actually n, right? This is actually n, and if n is large, then this product can be a pretty reasonable number. It need not be infinitesimally small. Now, if you add another extra 8j to it, so that two spins are flipped. So suppose you have 2 delta E, so delta E was 8j. Now, ground state plus 2 spins are up. Then the number of microstates that are possible, and this spin can be in any of the other microstates, so it's n into n minus 1 by 2 factorial, and that's again a huge energy. So this number is going to be multiplied by exponential 2 delta E by kBt, right? And it is this product is what is going to decide what is the energy of the system. Each microstate, agreed, has a very low probability, but number of microstates into probability of occupying that microstate can have a pretty reasonable value. It need not be negligible. In fact, it will choose, it will take, this system will take energy from the system so that this product is maximized. I mean, total number of microstates, total number of microstates of the entire system, which in turn basically will decide what energy that this system is going to take. So this is something to chew about. We'll continue about what will be the width of this maxima in the next class, but I hope that you have got some intuitive idea about why the probability that the system will be in a microstate with energy Es is e to the power minus Es by kBt, but yet the system can be in a microstate with relatively with the energy Es, which can be large with respect to kBt. The probability that the energy Es need not, that the system is an energy, sum over all microstates, need not be infinitesimally small, because it's a balance, because what decides the equilibrium is the product of the number of microstates of the system and the reservoir. And this is the take-home message, why it is e to the power minus Es by kBt. Okay, so with that, I'll end today's class right now.